This video is a continuation to the previous one, which dealt with physical quantity and its measurements and its value, in addition to the dimension of this physical quantity. Here we're going to put some emphasis on the importance of the dimension of physical quantity. One of the important applications of dimension is to check the correctness of a physical equation. The existence of physical quantities in a mathematical equation in physics allows us to check such equation by using dimension. Once the dimensions of the existing physical quantities are the same on both sides of this equation, this means that such equation is dimensionally correct. Now, if you have an equation like this, which says that the distance equals the velocity multiplied by time, and you want to check whether if this equation is dimensionally correct or not. Well, first of all, you need to write the dimension of each term of the physical quantity correctly on each side of the equation. If it turns out that the dimensions on the left-hand side of the equation are the same as the dimensions on the right-hand side of this equation, this means that your equation is dimensionally correct. Now, in this example, we need to elaborate. The dimension of distance on the left-hand side is the length, while the dimension of velocity on the right-hand side is L over t, while the dimensions of t is t. Thus, the consistency requires that the dimension of the distance on the left-hand side must be equal to the dimension of the product of velocity and time. Substituting the dimension of each physical quantity, you will get the dimension on the left-hand side is equal to that on the right-hand side. Thus, you can say that the equation is dimensionally correct. Let us take another example on dimensional analysis. This example is about a particle moving in a uniform acceleration along the x-axis. This example consists of two physical equations of motion which are presumably correct. We need to show whether these equations are dimensionally correct or not. In part A, the final velocity of the particle equals the initial velocity plus the product of the acceleration and time, while in part B, the square of final velocity equals the square of initial velocity plus twice the product of the acceleration and displacement. So we need to check the dimension of each term on the left and right hand sides. On the left hand side, the velocity has the dimension of L over t. On the right hand side, where there are two terms, the first term for the velocity, initial velocity, which is the same as that on the left hand side, which is L over t, and the other term is the product, the dimension of the product of A and t, which is equal to the dimension of A multiplied by the dimension of t. Knowing that the dimension of A is L over T squared and the dimension of T is T, then the product of this gives us L over T. The left-hand side, again, equals the right-hand side, and the equation is dimensionally correct. In part B, on the left-hand side, the final velocity has the dimension of L over T squared. On the right-hand side, again, we have two terms. The first term gives us the dimension of the square of the velocity, which is L over T squared. And the product, the second term, is the product of acceleration and displacement. The dimension of acceleration is L over T squared, while the dimension of displacement is L. Then this equals to L over T squared. Now we have again the left-hand side equals the right-hand side, and the equation is dimensionally correct. Another use of the dimensional analysis is such analysis enable us to find unknowns in a formula or a physical equation. But in this case, we have to consider at the first beginning that the left-hand side and the right-hand side are equal each other in order to find the unknowns. For example, to find the exponents n and m in the formula of position of a particle x, which is proportional to a, the acceleration, to the power n, times the time to the power m, where x is in meters and a in meter per second square and t is in seconds. To do that, we have to consider that the given formula is only correct when left-hand side equal to the right-hand side. On the left-hand side, x, which is the position of the particle, has the dimension of L, while on the right-hand side, the dimension of the product of a to the power m times t to the power m is actually equals to the dimension of the acceleration to the power n times the dimension of the time to the power m. Since left-hand side equals right-hand side, then L equal L to the power n over t to the power n multiplied by t to the power m. This equation must be equal. So we have to equate the exponents of L on both sides in order to get the value of n, which turns out to be equal to 1. Also, equating the exponents of t on both sides of equation will give us the relation minus 2n plus m equals 0. Knowing that n is equal to 1, this gives us the value of m, which is equal to 2. And our relation now becomes x proportional to a t squared. Must be noted that this equation is one of the equations of motion of a particle moving in a uniform acceleration when the initial velocity considered 0. Here, the factor, the fraction half, is the constant of proportionality, which is dimensionless in our case. Another application on the dimensional analysis is an exercise, and you are asked to find the exponent of n and m in the formula of circular motion, where the acceleration is proportional to r, the radius, to the power n, multiplied by the velocity v, or the speed v, to the power m, where a, again, is the acceleration of a particle moving in a circle of radius r with a constant speed. If you work out this problem, the answer should be m equal 2 and n equal 1. In another application for the dimensional analysis is to find the dimension of the unknown physical constant, again by using the dimensional analysis. And in such case, the left hand side must be set at the first beginning equal to the right hand side. An example of that, what's known as the inverse square law for the force of gravity between two objects separated by distance r, having two masses, small and big M. If the force units given as kilogram meter per second, you are asked to find the units of the proportionality constant G. Again, the left hand side is set equal to the right hand side of the equation. F force equal G as product of the two masses over the square of the R. And the left hand side given kilogram meter per second square for the force. On the right hand side, G is the dimension wanted to be found. The two masses each has a unit of kilogram. This is divided by meter square, and meter is the dimension or the unit of the radius. From here, G has the dimension of cubic meter per kilogram second square, or in terms of the standards can be written as cubic L over mt squared. G here is known as the universal constant of gravity. This is another exercise for the students and should be solved at home. You are asked to find the constants a, b, and c, the dimension of these constants in this equation. X equal a plus b t squared plus c t cubed, where x is the position of particle in meters and t is the time in seconds. The answer is the dimension of a will be meter, dimension of b will be meter per second square, and the dimension of c equals meter per cubic second. Let us test our understanding of the dimensional analysis by these simple questions. Question 1. Does the dimensional analysis provide the numerical values of a constant that may exist in an algebraic equation? Well, the answer, no, it does not. Question 2. Does the dimensional analysis provide the units of any constant that may exist in any physical equation? The answer is yes, it does provide the units of that physical constant wanted in the physical equation. Question number 3. If an equation is dimensionally correct, does that mean the equation is algebraically correct? The answer is no, it does not mean that the equation is algebraically correct. Question 4. If an equation is not dimensionally correct, does that mean the equation cannot be true? The answer is yes. It means that the equation cannot be true. Question 5. If the exponents of any physical variables can be obtained from an equation, does that mean the equation must be dimensionally correct? Answer, yes. This means that the equation must be dimensionally correct. Regarding the conversion of units, we're going to follow a very simple solving strategy in this. If we have 5 kilograms of mass wanted to be converted to grams, how can we do that? Step 1, we'll start by recalling the conversion factor, which says 1000 gram equal 1 kilogram. Number 2, form a unity out of it with the known unit and the denominator. It means we can divide both sides of the equations in number 1 by 1000, then 1 is going to be equal to 1000 gram over 1 kilogram. Step 3, multiply the units by 1, which is 1000 gram over 1 kilogram. Then we're going to have the kilograms cancelled in the denominator and numerator, and the result will be 5000 gram. Another example for the conversion of units, if the official old land speed record is 1228 km per hour, which is set on October 15, 1997 by Andy Green and the jet engine car thrust SSC. So you are asked to express this speed in meters per second. So following the same strategy as before, by recalling the conversion factor of kilometer to meters and hour to seconds. Step 2, set 1 for each conversion factor. So for the first one, 1 equal 1000 meter per or over kilometer, and for the time, 1 equals 1 hour per or over 3600 seconds. Then step 3, multiply the speed you have in kilometer per hour by 1 for the conversion of meters to kilometers to meters, and 1 for the conversion of hours to seconds. For the first one, we have 1000 meter per 1 kilometer. For the second one, we have 1 hour, 3600 seconds. Then the results will be simply this: 341.11 meter per second. The uncertainty, which represents the error expected in a measurement. For example, if you want to measure the width of a room, classroom, if we used a ruler and it turns out to be 10 meters, but it can be 10.2 meters or 9.8 meters. This means that the width of the room is 10 meters with an error of a plus minus 0.2 meters. This plus minus 0.2 meters is called the error or the uncertainty in the measurement. So in this case, if the width of the room is 10 meters, the error or the difference or the uncertainty in the measurement is 0.2. The absolute error is 0.2 meters as well, because this one might be plus or minus. So in such case, the absolute error will be just 0.2 meters. The fractional error, which is the ratio of the absolute error to the width, it has no use, is going to be 0.02. If we want to find the percentage error, we just multiply the last fractional error by 100. So we'll get 2% of error in the width measurements. Regarding these significant figures, again using a ruler to measure the length of the book, and it turns out that this book has a length of 25.3 centimeters. The question, how many figures here? We have 3 figures, 2, 5, and 3. So which one of those figures are significant? Which one of those figures is significant and which is not? For the first one, there is no doubt the first figure is correct. The first digit is correct. And there is no doubt also about the second digit, 5, which is correct. The third digit can be different, but not totally wrong. So there are 3 significant figures in this number, or in these measurements. If you are asked what is the distance between Amman and Erbil, so the calculated distance is 92.21 kilometers. Question, what is the significant figure of this result, of this resulting measurements? The first 2 are significant. Well, the one after the decimal, there is some error in this, but it's still within the significant value, while the third one could be, which is, I mean, the measuring process is much bigger than this digit, so it's not significant in this case. And then we will have the result is this. It is very important here to mention that the number of significant figures in the final answer of the product or division of different quantities should be the same as that in the quantity having the smallest number of significant figures. Concerning the addition and subtractions of numbers, also the number of decimal places in the final answer of addition or subtraction process is equal to the smallest number of decimal places of any term in the process of addition or subtraction.